This video presentation will outline the notes for section 16.4 on the pH scale, as well as 16.5, calculating the pH of strong acids and bases. Before you begin, make sure you have your notes in front of you as well as your calculator. I would encourage you to pause the video at times so that you can write material down. To start out, we have a science and chemistry joke. Why do chemistry teachers like to teach about ammonia? Because it's basic material. I'm sure there's crickets right now, so we will move on. 16.4, the pH scale. When we start talking about pH, and you classify a solution as having a certain pH, the pH is actually a measure of the acidity or basicity of a solution. And there's certain pH ranges, below 7, above 7, and equal to 7, and we'll be talking about each of those in a moment. To calculate the pH, the equation used is negative log of the concentration of H plus, or hydrogen concentration. Now on your calculator, make sure you are using log base 10 and not natural log. As we start working with pH and pH scales, keep in mind what that log base 10 scale is telling you. This equation is based on a logarithmic scale, which means a change in your concentration of H plus by a factor of 10 causes the pH to change by 1 unit. So sometimes kids will use pH paper to measure two solutions, and they'll say one is 4 and one is 6, and they'll say, well, it's only two different spots on the pH scale, when in actuality, in terms of their hydrogen ion concentration, 2 spots would actually be 10 squared, or a difference in 100 times of a factor that the H plus is changing. So keep in mind it is a logarithmic scale, not just a 1 by 1 unit scale. This logarithmic scale requires us to use a little bit different sig figs than we are used to. And the rule is for logs, the sig figs is determined by the number of decimal places in your pH. However many decimal places are in the pH has to be equal to the number of the sig figs in the molarity. And we'll kind of talk about this as we start actually doing some calculations. If we reference the values for the pH scale and what they are telling us, in acidic solutions, the concentration of H plus, if it's greater than 1 times 10 to the negative 7th, the pH will be below 7. And if you put into your calculator negative log 1.0, use the EE button and put in negative 7, you should get a pH of 7. So in acid solutions, we have a greater hydrogen ion concentration. In basic solutions, you can say your hydroxide is greater than 1 times 10 to the negative 7th, or you can say your hydrogen ion concentration is less than 1.0 times 10 to the negative 7th. So for bases, our pH is greater than 7. The majority of pH values will fall somewhere between 0 and 14. It is, on occasion, we will have a strong acid and a high concentration of that strong acid where the pH can actually be negative, but typically they will fall somewhere in that 0 to 14 range. Now pH is calculated by taking negative log of H plus concentration. There are other scales that look similar to pH. They also have that lowercase p. If you have really that lowercase p, it does imply a certain type of mathematical relationship. So in general, for any number x, if you put a p in front of that x, it really means to take the negative log of that number value. So just like pH is negative log of H, if instead we are working with a base solution and we have an OH concentration, then the POH is equal to the negative log of OH. If we build upon what we learned about previously about acids and bases and water ionizing into H plus and OH minus, we know that the concentration of hydrogen times hydroxide is 1 times 10 to the negative 14th. Well, if you did negative log of both of those sides, you would end up with a relationship that shows us how pH and pOH are related, and they do add up to 14. The reason this might be useful is that if somebody tells you the pOH for a solution is 4.32, well, nobody really thinks in terms of pOH. Most people anyway, they always think in terms of pHs. So if you're given a pOH, you can subtract it from 14 to determine the pH. And then that's a common reference point for most people, because if the pH is below 7, they know it's acidic. If the pH is above 7, they know it's basic. And if it's equal to 7, then it's neutral. Some other handy formulas, if instead of going from concentration to pH or pOH, if instead we're asked to find concentrations, then two other useful formulas would be concentration of H plus is 10 raised to the negative pH, and concentration of hydroxide is 10 raised to the negative pOH. So I would make sure somewhere in your notes it's very clear that you have all these formulas in some nice boxes so they're easy to find. pH is negative log of H, pOH is negative log of OH, the two of them add up to get equal 14, and then H plus is 10 raised to the negative pH, and OH concentration is 10 raised to the negative pOH. We are going to take a moment to calculate some of the values in this table. And if we work, we'll look at the first row going left to right, and then I will have you pause the video and try the rest of them. So if we are given pH, if I take and subtract that number from 14, and you can do this along with me on your calculator, 14 minus 3.24 means that the pOH is 10.76. Remember, these two columns add up to 14. If we're trying now to get the H plus from that, we need to take 10 and raise that to the negative 3.24 power. And since I have two numbers in my, two decimal places in my pH, that means my H plus has to have 3 significant figures. So I'm going to go with 5.75. Oh, sorry. 2 decimal places, 2 sig figs. So 5.8 times 10 to the negative 4th. Now for OH minus, sorry, little interruption there. So if we are given pOH, we have really 2 ways to get the OH minus concentration. We can do 10 raised to the negative 10.76, or knowing that kW is 1 times 10 to the negative 14th, you could take 1 times 10 to the negative 14th divided by H plus to get your OH minus concentration. And so the answer should be 1.7 times 10 to the negative 11th. I would suggest that you pause the video and go ahead and work through the remaining boxes using the formulas that you have, and then unpause the video to check your answers. So hopefully you've had a chance to try these. The pH worked out to be 7.77 for the second example, H plus 1.8, 10 to the negative 8th, OH minus 5.9, 10 to the negative 7th. Third example, pH 4.611, pOH 9.389, and OH minus 4.083 times 10 to the negative 10th. Last example, pH 11.057, pOH 2.943, and H plus 8.77 times 10 to the negative 12. Now, one thing that you may kind of notice is you can at least check to see if your answers are reasonable by taking a look at, sorry, interrupted again. I think I was talking about the exponents on these. If you take a look at the exponents in each example, when you have decimal type numbers as your concentration beginnings, like 5.8, 1.7, 2.45, not like 1 times 10 to the 5th or 1 times 10 to the 9th, but just these kind of random decimal numbers, you notice that the exponents do add up to negative 15 in each case. And so that's kind of a way to check if your H plus and OH minus are where they're supposed to be. Just like pH and POH add up to 14, these will add up to negative 15. Now, this table is just for reference, kind of some common materials in a range of both acidic and basic materials. And if you look at this center column, as your pH goes up, your POH goes down. They're inversely related because they both add up to 14. Now, having said that, I certainly look at the pH column more than the POH column when I'm trying to judge if something is an acid or base. And some common substances just to be aware of, I mean, we have water at a pH of 7 or neutral. Baking soda is slightly basic. We always think of it, you know, reacting with vinegar, or that which is an acid. We have ammonia and bleach and sodium hydroxide in the basic range. Up at the top, gastric juice, your stomach acid, is actually a dilute mixture of HCl. So sad to say and disgusting to say, but when someone throws up or gets sick, you have that funky, sour smell. It is because of the HCl that your stomach is secreting. Lemon juice too, certainly colas. Your dentist warns you not to drink too much pop because it's bad for your teeth. And so having that phosphoric acid in the cola in contact with your teeth is not good for it. And so there's just a range, just some common substances of their pHs and POHs. One of the things Dr. Hansen has included on the test in the past is a table where you have to estimate pHs without a calculator. And this is actually a table from an old test of his. And I would like to kind of go through with you how this table works. And so you can use your H plus concentration and pH to help. If you have one column, you can find the other column. And so starting with HCl, this number 0.001 is the same as 1 times 10 to the negative 3. Now because pH is a logarithmic scale, you can look at that power of 10 to determine the pH. So if it's 1 times 10 to the negative 3, then the pH would be 3. If you have a solution that's a pH of 5, your H plus concentration will be 1 times 10 to the negative 5. A solution with a pH of 9 would be 1 times 10 to the negative 9th. Now, be careful because sometimes you will be given a base instead of an acid. Now, in a potassium hydroxide solution, your OH concentration is going to be 1 times 10 to the negative 2nd. And the POH, therefore, would be 2, which means your pH will be 12. If your pH is 12, the H plus is 1 times 10 to the negative 12. So I certainly want you to see the correlation between the pH value and this negative exponent. This is a little bit different than the table that we looked at previous, where the exponents added up to negative 15. That's because these were random decimal numbers. In the table Dr. Hansen's going to give you, they will all be just the value of a power of 10 or exponents. So they'll all be 1 times 10 to some power. And if those are the types of numbers you're working with, then instead of adding up to negative 15, these numbers are going to add up to be negative 14. And so if your H plus is 1 times 10 to the negative 3, your OH will be 10 to the negative 11. If your H plus is 1 times 10 to the negative 5, then your OH would be 1 times 10 to the negative 9th. And so this is a table, and we will practice these, as we get closer to the exam. But this is a table you should certainly expect to see and be able to complete without a calculator. Now, this slide is going to talk a little bit about ways to measure pHs. Certainly we have electronic pH meters, and some of the labs we have coming up using the LabQuest, we will use a pH probe. Certainly in the lab as well, and in other courses, you've probably used different indicators. And indicators are just dyes that change colors as the pH changes. Certainly some of the ones you've probably looked at previously are phenolphthalein, which is colorless in acids, and then that bright beautiful magenta pink in bases. We've also used bromothymol blue, and when we did a titration, when we were in the acid range, it was yellow. It was green for a very narrow band in the middle, and then blue after that. Depending upon the purposes of what you're working on in the lab, we have color changes that can occur really at a variety of ranges of pHs. There are also, in addition to indicators that we see in the lab, there are also some natural indicators out there: red cabbage juice, tea, mustard. Many of them will change colors in acids and bases. And red cabbage, you can either boil it and collect the juice, or you can put it in a blender and mix it with some water, and you can get a variety of color changes with that as well. Now, this next slide, I have to put a disclaimer out there. You know, sometimes you watch the news and they say, warning, you know, the images are going to be graphic and disturbing. Well, I have a picture of a foot, a person who wore open-toed shoes during lab. Now, it was not a Delano student or even a person I know. It was just a safety conference that I went to. They gave us this, showed us this picture, and I asked if I could use it to show my students to stress the importance of wearing proper safety attire and appropriate clothing. So I won't leave it up there long, but this is an image of a person whose foot was burned badly by acid. And you can see it's several layers thick and not very pleasant to look at, so just keep in mind, since acids are so corrosive, we want to wear closed-toed shoes when we work with them. All right, our last section then, section 16.5, strong acids and bases. Strong acids and bases, as we talked about in chapter 4, are considered to be strong electrolytes. And what that means is that strong acids and strong bases ionize or dissociate completely, 100% in solution. And I have an example of an equation of each. You could write nitric acid, which is on our strong acids list. It will dissociate 100% into H plus and NO3 minus, nitrate. We also have sodium hydroxide, which is on the strong bases list. It dissociates 100% into sodium plus 1 and hydroxide minus 1. Now, the reason we bring up strong acids and bases again in chapter 16 is that we will have to use two different approaches to estimate the pH of acid and base solutions. We will use one approach in this section for strong acids and bases, and later use an equilibrium or icebox approach for weak acids and bases. So when you look at a solution of a strong acid, the only place those H's are coming from is the acid itself. And if you can figure out how many H's are present, we can then get the pH of that solution. And oftentimes, if you know the molarity of the acid, then you can get the molarity of, the pH of that acid. So let's say we have a 0.015 molar solution of HBr. HBr is on our strong acid list. So HBr, as it dissociates, will 100% split into H plus and Br minus. Now, the ratios are really our key, and since it's a 1:1:1 ratio, if this concentration is 0.015, then we know the H plus and the bromide minus are also 0.015. The concentration that is relevant for us is certainly the H plus. And so previously we were given a formula that pH is negative log of our H plus concentration. And so if you type into your calculator negative log of 0.015, you get a pH of, and that has 2 sig figs, so I would go with 1.82. And if you think about this, this number, 0.015 is between, I look at, it's 1.5 times 10 to the negative 2, so it should make sense that our pH is in the ballpark of 2. So for strong acids, whatever your initial concentration is for the acid, you would use that number to calculate pH. For bases, since we're working with hydroxide, then we have the pOH. and then therefore the pH of a strong base, is also calculated from the initial molarity or concentration of the base. Now this time around, because we have some strong bases that have 2 hydroxide ions, that gets a little bit tricky with the stoichiometry, and I will show you one example of each. So for a 0.0025 molar solution of KOH, as this KOH dissociates, we will get potassium ions and hydroxide ions. And again, similar to the acid, everything is in a 1:1:1 ratio. And so if the if the KOH is 0.0025, the potassium ions will be 0.0025, as will the hydroxide. Now, the hydroxide is what we're interested in. We can calculate pOH for that solution, negative log of the concentration, 0.0025. So if we crunch that out, negative log 0.0025, we get a pOH, careful, we're not done yet, a pOH of 2.60. However, we know that pHs for bases should be above 7. So remember, you have to subtract it from 14. You could probably do this in your head. And you'd get a pH of 11.4. So remember, whenever you're working with bases, you find the pOH first and then subtract from 14. I'd also like to look at an example with calcium hydroxide, CaOH2. And the reason why this one is just a little bit different is that as it dissociates, you will get calcium ions and 2 hydroxide ions. So if the initial molarity is 0.0015, the calcium ion concentration will be 0.0015, but the hydroxide will be 0.0030 because of the 1:1:2 ratio. Now that we have that hydroxide concentration, we can do pOH, negative log of 0.003, and that gives us a pOH of 2.52, and then if we subtract that from 14, we'd get 11.48 as a pH. So one of the nice things about working with strong acids and strong bases is that if you know the concentration, then you just do negative log and either get your pH or your pOH, and it's a very straightforward calculation. Our last slide will provide you some examples, so I would encourage you to again pause the video, crunch out your numbers, and then check it. All right, so you can check your work. The first one, 0.078 molar HCl, has a pH of 1.11. The second one, 2.82. Make sure you check the third one. In the third example, since there are 2 hydroxide ions in this one, I would take 2 times 0.0020 to get a concentration of hydroxide of 0.0040, and then take the negative log of that, and then subtract from 14 since it's a base. That one had a pH of 11.60. The last example has only 1 hydroxide ion, and so you would take the negative log of 0.0125 and subtract it from 14. But because this one, the concentration has 3 significant figures, then the pH should have 3 decimal places. That's it. Please email me or stop in if you have questions, and enjoy the rest of your day.